Hi, welcome to the session 18A, visualization. We are going to start with Inga Schlegel, did I pronounce it right? Tie your data, a tool for combining data of different spatial granularity.
Thank you for this introduction. My name is Inga. I'm a research assistant at, or within the lab for geoinformatics and geovisualization at the Hafen City University in Hamburg. And I would like to start with a little story. This is Paulo. He originally comes from Lisbon and plans to move to Hamburg for the sake of love. This is Hannah, his girlfriend, and she already lives in Hamburg. The two are looking for a new flat in Hamburg, and because Hannah is a restless sleeper and kind of scared, the two want to move to a city district where number of apartment break-ins are minimal. So Paulo asks the local government for appropriate information concerning their preferred circumstances for their house hunting. Thanks to the open data law of the city of Hamburg, he receives this map here, which shows the absolute number of apartment break-ins for each of the 27 police departments of the city. As the two want to live within the safest city district, the amount of break-ins within the chosen district should be at a minimum. The problem is, the data concerning the break-ins are not defined per city district. It's the spatial units of police departments, so a completely different reference area. So how can we bring this information of break-ins to another spatial reference area so that we can help Paulo and Hannah identifying the best city district for them? Usually, when we want to aggregate several rooms into one, we just add up the values of the smaller rooms, here in purple on the left-hand side, to a new value for the larger, here the orange room. So, assuming that the city of Hamburg consists of 5 zones of population and that there was a large immigration wave as well, and we want to merge them into only 2 zones, it's simply 1 plus 4 equals 5 inhabitants for the left orange zone, and 1 plus 2 plus 1 equals 4 inhabitants for the right zone. In the opposite case, which means transforming numerical values from larger to smaller zones, we take the common surface area of the larger zone, called source zone. This is the purple one on the left-hand side, and is therefore identified by S, and the smaller so-called target zone on the right-hand side in orange here, which is ST, this common surface area. We put this into relation to the area of the source zone, the purple one, and multiply by its original data value, so 5 inhabitants in our case. For Paulo and Hannah, the transformed information concerning the number of apartment break-ins from police departments on the left-hand side to city districts looks like the map on the right-hand side. What we've done here is we simply redistributed the data values from larger to smaller polygons. We do this kind of usual aerial interpolation if spatial data sets are arranged in a hierarchical manner. So that means that all of the implemented data sets feature the boundaries of the data set with the largest zones or polygons, like in this example I talked about before. For all other cases, and especially for non-hierarchical data sets, like the two available for Paulo and Hannah, we developed a free and open source tool to transform and to combine data of different spatial granularity. The tool is also called CoGran. Non-hierarchical means that the polygon boundaries of the two applied data sets do not coincide. So that's it. Okay, that's it. Our tool allows you to choose between several calculation methods for this transformation of geodata from one spatial unit into another, no matter if from smaller to larger or from larger to smaller zones, or if it is hierarchical or not. Depending on the calculation method, the data values are redistributed by different weightings, so that the results all look a bit different in comparison to each other, what you have seen here. Okay. This means the calculation methods do not only include this usual areal interpolation, which is based on common areas, but you are also able to include additional information to make your data transformation more precise. For example, adding a binary data set which filters the input data and only considers, in this particular case, inhabited areas, makes our conversion more accurate. You can expand this binary mask by involving percentage values of these inhabited areas, and this so-called n-class mask, where n is a number of classes, supplies an additional weight, assuming that, for example, 10% of all inhabitants of the city of Hamburg live within the bright gray areas, and 10% live within the darker ones, and 30% or so live in the darker ones, and so on. However, less information needs a data redistribution via linear regression. This method transforms your data on the basis of different weighting classes in the absence of any class values. Instead, this can simply be numbered classes from 1 to whatever, representing, for example, densely populated areas or sparse populated areas. I won't go into any further detail concerning this method because that would be too complex for the last conference session. A fourth possibility exists if you are lucky and your target data set, so the city districts in our case, contains an additional attribute like the absolute number of inhabitants. And all of these four shown methods are able to process an extra weight concerning the data values, an extra weight concerning your data values for more precise transformation results. So the important thing about it is that choosing the most appropriate method strongly depends on the individual dataset's characteristics. We provide the tool on GitHub so that you just have to download the software and be familiar with only, and that's true, the most essential command line basics for an execution. I'll show this once again, so don't worry. The coding language is JavaScript within the runtime environment Node.js for executing the program code. To make use of additional functions, we implemented several JavaScript libraries, like turf.js for geographical queries, and also D3, which is actually a library to create gorgeous data visualizations and is often used by journalists and information designers. The third and last library provides, as the name suggests, simple statistics, and we primarily use simple statistics to perform regression analysis within our program code. Right at the end, as already mentioned, we published our tool on the platform GitHub, but it's still in progress there. We developed this tool in cooperation with a German local news desk, and unfortunately, I'm a bit afraid to say that, their common language or coding language is JavaScript. However, our primary objective concerning our program code was correctness and not performance. So the regretful thing about the JavaScript code is the data transformation really takes a long time, so that you even have the feeling that the performance tortoise moves backwards. As this is not the desired result, we later decided to transcribe our program code from JavaScript into Python, also with the aim of developing a QGIS plugin at the same time. There, we implemented a spatial index, and surprise, the performance rabbit is much faster than the tortoise. In this graph here, you can see the runtime of 4 of our implemented calculation methods, while their complexity increases downwards. So this is also the reason why the runtime increases in that direction. The data underlying here is the one from Paulo and Hannah, so just as a reminder, from 27 polygons as police departments into 104 city districts. This is another example pointing up that first, Python is not the appropriate choice in any case, but in most of them. And second, the execution via JavaScript is a question of lots of minutes and can even take up to a day. We also decided to implement this Python version due to TERF's limitation regarding geodata formats. It only allows GeoJSON and therefore WGS84, and also some other geometrical problems which turned out for our application. At the moment, the QGIS plugin together with the Python code is in progress, so that command line layman and other enthusiasts of graphical user interfaces will be able to easily make use of the tool. Nevertheless, we are also planning to provide a simple graphical user interface for the JavaScript version, and a further improvement for this program code, for the JavaScript code, is doubtless the inclusion of a spatial index. The usability gets further enhanced by user support for choosing the appropriate calculation method for the individual data sets. And we will also be able to implement additional ideas within our third research project in a row, which is approved and scheduled for this year. And the focus of this project will be on the integration of information on uncertainties to further support the user's decision process. Last but not least, if you want to know where Paulo and Hannah should move to, it depends, but the city center looks quite good. But one thing I can tell you, both of them are happy, and if you want to download the tool now, here's the link once again, and thank you for your attention.
no one, I just want to mention that I think this relates a lot with the keynote from this morning, because if different interpolation methods give so many different results, that means that you should know it's not just a wizard of adding data here, 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 and next, 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 and then see what, you have to understand what the algorithm is doing.
Yeah. That's also the reason why we want to give this decision support for the users.
So no questions? Should we move to the next one? Okay.